Hi guys! Today we are going to speak about
Chemical bonding!
We are the
Chemical Bonding Brothers!
Ionic bonding, covalent bonding, metallic bonding. Mr. Yap, there's so many types of chemical bond.
Yeah.
Right, let me ask you a question.
Okay.
Which is the strongest chemical bond?
Must be ionic bond lah.
No.
Then metallic bonding.
No.
Then must be covalent law.
No. You want to know the answer?
Hey, tell me that.
Okay, I'm going to tell you the answer. The answer is James Bond.
Okay.
Okay, jokes aside, alright? Now, chemical bonding is actually one of the most important chapters all the students will learn in JC1. So maybe let's give the students an overview what to expect in this chapter, right? So as you flip to your notes, you will notice this is the overview of chemical bonding. Generally, there are two types of bonding that we are looking at. Now, the first one are those that involve lattice bonds, right? So lattice bonds will involve very strong forces, and there should be things that you are quite familiar with. For example, your ionic bonding, giant covalent bonding, as well as metallic bonding.
Right? And on a smaller scale, between the molecules, there exist intermolecular forces of attraction, which you'll be familiar with from your secondary school days. But in A level, we're actually going to learn three different types of intermolecular forces of attraction. And they are instantaneous dipole, induced dipole interactions, or what we call ID-ID interactions, permanent dipole interactions, or what we call PD-PD interactions, and the third type is actually called hydrogen bonds. So we will delve into this in greater details in subsequent lessons, so stay tuned to that.
Hey, Mr. Yap, let's do something that they are very familiar with first. Okay, so let's begin with ionic bonding.
Okay.
Now, I heard you're an excellent teacher.
Okay.
All right, but actually, I find someone who can teach better than you.
Oh, really? Show me this.
Yes, all right. So I'm going to introduce two new teachers to the class today. Right, the first one we have here is sodium. And then we also have chlorine. So as you can see, sodium is a metal, and metal, they like to lose electrons, whereas non-metals, chlorine, they like to gain electrons. Okay, so I'm going to show you a video of how we actually do electron transfer between them. Right, so you take a look at this. What's happening now is chlorine is very interested in the valence electrons that sodium has. All right, so what is he going to do? Right, he's going to snatch or steal the electrons away from sodium. So the end result is a transfer of electrons from the metal towards the non-metal, and then you have one of them being the cation, which is the sodium, and then the other one who is going to be the anion, which is the chlorine. So this is what happens, a transfer of electrons between them, and they end up as stable species. Pretty impressive, right?
Yes, pretty impressive. I mean, the dogs are cute, just like you.
Yeah.
But you can't bring the dogs to your exam, right? So
yeah.
let me show you how to explain it during the exam.
That's true. Mr. Yap is better. Okay, let him do the work.
All right, so the sodium is a metallic element. It tends to lose electrons to achieve the stable noble gas configuration, thereby forming cations. The electron loss are gained by the non-metallic chlorine, forming anions. And the ionic bond, therefore, is described as the electrostatic force of attraction between a positive ion and a negative ion. All right? So we would say the ionic bond typically forms between a metal and non-metal because of a large electronegativity difference, causing the electron transfer to come from the metal to the non-metal.
Hey, wait. What is electronegativity?
Simple. Electronegativity is basically the ability to suck electrons to yourself. Yeah?
Okay.
So chlorine is very electronegative.
Okay.
So it will suck sodium's electrons away from sodium. So we would say that chlorine is a sucker.
Oh, sucker.
Yeah,
Hey,
sucker.
why you use suck? Can we use the proper terminology?
Okay, so the proper definition of electronegativity is the ability to attract bonding electrons to yourself. So if an element is very electronegative, we would say that it has a high tendency to attract bonding electrons to yourself.
Alright, now let's take a look at something I think they are quite familiar with, which is a dot and cross diagram. Okay, there are two examples in your notes. I think we're just going to use aluminium fluoride as an example to explain this to the class. So as you can see, what is happening here is there will be a transfer of electrons from the metal towards the non-metal. So that's why fluorine became an anion, and then you just combine them together to form an ionic compound. But guys, if you take a very close look, there are some differences when you move from secondary to JC dot and cross diagram. So if let's enlighten them, right? What is the main difference between secondary and JC dot and cross diagram?
Alright, in fact, there are two main differences. So the first one is we no longer use circles to represent electronic shells. So you see there are no circles around the cation and anion. And the second thing that you have to take note of is, in terms of the metal ion, after losing its valence electron, that shell is technically empty, so there's no longer a need to label electrons around it. So your metal ion will usually look very bare, so you just enclose the chemical symbol in a square bracket with the charge reflected on the top right hand corner.
Yep, that's right. So there's a main difference between your secondary way as well as your A-level way of drawing the dot and cross diagram.
Alright, so if you were to look at the diagram on the right hand side of the notes, you will notice that this is your typical ionic crystal lattice structure. So what you should pay attention to is the arrangement of the ions. It's arranged in an alternate manner, whereby the negative ion is beside a positive ion, which is also beside a negative ion, and the pattern goes on. So this alternate arrangement of ions will allow the electrostatic force of attraction to be formed between the positive ion and the negative ion. So William, let me ask you a question.
Sure.
Why must they adopt this alternate arrangement of ions?
Well, they are alternating because you have plus, minus, plus, minus. This will allow them to maximize attractive forces. Otherwise, they are just going to repel, right? And then they're going to break up away from the ionic bonding. Now, another thing you notice, guys, if you look at the last bullet, you will notice this word that says that, or this phrase that says ionic bond is non-directional. Now, what is non-directional? It means, imagine you have a cation over here. It doesn't really matter where my anion is. It can be here, 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 or here. We are just going to attract it equally strong in all directions. So that's what we meant by non-directional. All right? Now, why don't we just test them on something simple?
Hey, William, don't say test, you say test, they feel very stressed.
Oh yeah, we cannot use the word test. Okay, let's examine them.
Wow.
All right.
Okay.
Okay, right, guys. So we have examination for you right now. Okay, so we have 2 questions over there. Why not you do this? Pause the video right now. Try out the 2 questions. Once you're ready, just click the play button, and we're going to show you the answers. Welcome back.
All right. So I hope you guys have drawn the diagram. So the magnesium fluoride example is pretty straightforward, so you guys can just double check your answer. Alright, so let me try to explain to you the other compound, the indium oxide. So the indium oxide, when drawing the dot and cross diagram, the first thing you should do is to write down the ions first. So the indium ion and the oxide ion, you should be able to deduce that the indium has a charge of 3+, the oxide has a charge of 2-, and based on the formula, each formula unit contains 2 indium ion and 3 oxide ions. Now, indium is a group 13 element, so it has 3 valence electrons. So after losing those 3 valence electrons, you will form a cation with a +3 charge. So you enclose it in a square bracket with the charge label on the top right hand corner. Notice that I do not label the valence electrons anymore because that shell is now technically empty. Now oxygen is in group 16. There are 6 valence electrons denoted by my 6 dots. Alright, so it will gain 2 more electrons from indium to achieve the stable noble gas configuration, acquiring a charge of 2-. And the last thing you should do is to just add the coefficients in. So there are 2 indium ions and 3 oxide ions. Right, so this would be the dot and cross diagram for ion 203. Okay, so William, we always say that ionic bonds are a strong electrostatic force of attraction, right?
Yes.
How strong is strong? Do you know that actually we have a way to measure the strength of an ionic bond?
Yes, we do, right? So ionic bonds can actually be quantified by a formula. Now, before we look at the formula, maybe we'll introduce a definition of lattice energy to everybody first. Now, you see there's a box inside your notes, and there's a lot of words over there. Now, what it says is this: lattice energy is the energy released when 1 mole of ionic compound is formed from the constituent gaseous ions under standard conditions. Pretty lengthy definition, right?
Yep.
So what do you think the students should focus on?
Right, so they should focus on 2 important points. The first one is to form 1 mole of a solid ionic compound. So the stoichiometric coefficient in your balance equation in front of the compound, it should be 1. All right, and the second thing is the compound is going to be formed from ions, and the ions must be in the gaseous state.
All right, very good. Right, so if you take a look at this equation, if you want to do the lattice energy of magnesium chloride, so the way they write the equation is always dependent on the definition itself, right? So as you can see, the key thing is to begin with this part, make sure that there's only 1 mole of ionic compound, and then you begin to work backwards. For example, magnesium is a metal, so as a metal, you'll be forming cations. That's why we write here Mg2+, make sure it's gaseous, and then chlorine is going to be anionic, again, make sure it's gaseous. The last thing you will do is to balance the coefficient in front, but the main idea and the main intention is to keep this as 1 because the definition insists that it has to be 1 mole of ionic compounds. Alright, so this is one example. There's one more example on the next page. Let's run through this together with the class. Now, they wanted the lattice energy of iron 3 oxide. Okay, so this time round, what we do is we make sure we form 1 mole, okay, 1 mole of iron 3 oxide, Fe2O3, make sure it's in a solid state. and then you begin to work backwards. Iron in the gaseous ions should have been Fe3 plus gaseous, and then we have oxygen, which is going to be O2 minus gaseous. Last thing we do, balance the coefficient by writing a 2 and a 3 just to make sure that this is 1 mole of ionic compound. Quite simple, right?
Yeah.
So, Mr. Yap, you can see from the equation, the ions, they are going to combine together. So, can you share with us what happens when they combine together?
Right, so when the gaseous ions actually come together to form the crystal lattice structure, electrostatic forces of attraction will start to be formed between the ions.
Okay.
So this is a bond-forming process, and bond-forming processes releases energy.
Right.
And hence we say that the lattice energy is actually an exothermic process. And since if you were to understand this in the energy level diagram, the gaseous ions, they will be of a higher energy level than the ionic solid because they release energy to become the ionic solid. Hence, if you look at it in terms of the energy level diagram, it will look something like this.
Okay.
All right. So since the ionic solid is of a lower energy content, it is said to be more stable than the gaseous ions. All right. So in terms of the attraction, if the attraction between the ions are stronger, they will release more energy when they come together, and hence that will correspond to a larger magnitude of lattice energy. So in other words, if your lattice energy is large, the attraction between the ions are strong, and we can therefore conclude that the ionic bonds between the ions are stronger. So there exists this important relationship whereby the strength of the ionic bond is in turn proportional to the magnitude of the lattice energy, which in turn is seen from this simple mathematical relationship. So there are two symbols here. Q simply represents the charge, so Q plus is the charge of the cation, Q minus is the charge of the anion. So you can tell that the magnitude of the lattice energy is proportional to the product of charges. Okay, R represents the radius of the ion, so R plus is the radius of the cation, R minus is the radius of the anion, and the magnitude of lattice energy is now inversely proportional to the sum of ionic radius. So William, there are two factors, right?
Yes.
Which factor do you think is more important in explaining the magnitude of the lattice energy?
Okay, this is math. All right, so you can see that charges are being multiplied together, right? Radius are just added together, so multiplication has a larger effect. Therefore, the change in the charges is going to be more significant than the change in the radius.
All right, so in other words, charge is the more important factor in accounting for the magnitude of the lattice energy and hence the strength of the ionic bond. All right, so to summarize it in a simple sentence, the larger the ionic charge, the larger the magnitude of the lattice energy, the stronger the ionic bonds. All right, the smaller the ionic radius, the larger the magnitude of the lattice energy, the stronger of the ionic bonds. All right, so these two sentences over here.
Okay. All right, so this is how the formula of lattice energy comes about. I think what's more important is they can apply this to an exam question. Okay, so let me just walk you through sample questions you're going to find in exams. Now you can see below there are a few word examples. Okay, let's talk about the technique and the strategy behind this. Right, so the question is compare the melting point between cesium chloride as well as magnesium chloride. Okay, first thing we realize is both are ionic bonds. Right, so when it's ionic bonds, we have to use the formula for lattice energy, right? So you can see the strength of the ionic bond depends on the magnitude of the lattice energy, which depends on the formula that Mr. Yap has already gone through with us. Okay, also note the English compare. Compare means you will observe the difference, okay? Observe the difference between them. Now you do realize the anions, the Cl, are the same in both cases, right? So the anion is not going to be a factor in this case, we're just going to cross them out. And if you compare cesium, cesium is +1 and magnesium is 2+, so there are changes in the charges. Magnesium has a greater charge. And at the same time, if you check your data booklet, you look at the radius, you'll notice that magnesium has a smaller radius as well, right? So if you do the math with a larger charge as well as a smaller radius, the end result is the lattice energy is going to be higher, and that's why the strength of the ionic bond is also going to be higher. Right, so I mean, it's always just focusing on the formula, noting the difference, and you just do the math from there. All right. Okay, another example in part B, very similar. You do notice that the cations are the same this time around, so we're going to cut away the cations. Now, in fact, for the anions, the charges are also the same. Realize that, right? So in both cases, we're going to cancel away the Q minus. Therefore, the differentiating factor is just the radius. So if you compare chlorine against bromine, you will notice that chlorine has a smaller radius, and therefore the end result is that the lattice energy of NaCl is going to be bigger. So it's a very standard question, right? We find this in exams, so make sure you are aware how to approach the question. Once you know it's ionic compound, apply the formula of lattice energy and just observe the difference, and then you're going to get a full marks for this.
Yep.
All right. Okay. Now, we have some questions on the next page, which is like a mini homework for the class. Okay, so guys, I need you to try these 2 questions. Try it on your own, right? When you come back to class, our teachers are going to explain the answers to you in class.